Hey everybody. So let's learn some more transformations. The next one is another common one that you will actually use, and it's rotate. The idea behind rotate is we have some point here, let's say, and we want to rotate it around some angle, around the origin, some angle theta, like that. Okay? So we want to rotate a point around the origin. Now, I'm not going to get into the derivation of this. It's actually quite cool if you're interested. You can look it up and you can see how did they derive this, but I'll just give you the formula. And again, this might look familiar from your other assignment. So if I have a point P, I can calculate P prime X as point X cos theta minus point Y sine theta, and I can calculate the P prime Y very similarly with PX sine theta plus P Y cos theta. Okay, so I can calculate that. Awesome. And I'm gonna make a note here. You can check your favorite linear algebra text for the derivation. It's pretty cool. And I'll also say that this is a rigid body. Rigid. This is also a rigid body transformation. So that's it. So if I have a point and I want to rotate it around the origin, just like with the translation, we can't rotate over any random point, but I'll come back to that. If we want to rotate it around the origin, then we have to use this formula. So let's look at what it looks like in matrix form. Okay, so again, px cos y, py minus sine, so that my x becomes that. So I can just write that out actually. So px will be multiplied by cos theta, and then py will be multiplied by minus sin theta. Okay, and this is my vector here, px, py. And remember, we're in homogeneous coordinates, right? I'm actually going to lasso that and give myself some more space. Look at that. Can't do that in a whiteboard. Oh, and I messed up. It's okay. All right. And then the next line is going to be sine theta and cos theta times the y will give me the next one. And then I just populate my w's again, 0, 0, 0, 0, 1. And maybe I'll draw these a little nicer. Okay, so let's test it out. Let's do a matrix multiplication. So cos theta times px minus sin theta py, 0w. Cool. And the next one is going to be sine theta px plus cos theta py. Cool. And then the w1. Cool. So this is exactly what I showed right there. So that's it. So to rotate something about the origin, you just use this formula, and now we can use this matrix. And now that we have it in matrix form, we can combine it with the scale that we said earlier. You multiply them together and you'll get a matrix that does both. How do you rotate around not the origin? I'm going to come back to that. But because first we need to learn the next, I want to learn the next transformation. Let's learn translation. Now translation is the first one that we'll see where translation is the first one where we kind of need to use homogeneous coordinates to make it work. The idea is really simple. When I move each point in space by some delta, right? Delta x delta y. We often call these tx for translate and ty for translate x, translate y. That is, for every p in our list, p prime is going to be the old point plus tx, and then the old point plus ty. That's all that we do. This is also a rigid body transformation. Now, yeah, I'll just draw the diagram. Might as well. If I have a thing here and I want to move it to the origin, I translate by these minus values, but from the center, this way, it'll minus, and I'll end up with my with my object reoriented by subtracting that from each point. Okay. But how do we do this in matrix? That's interesting. Editor's pick. Huh. Didn't even know I signed up for news. All right. So I got lost there. Yeah, but how can we do this using matrix multiplication? It's actually pretty tricky. And the reason it's tricky is because we're multiplying, but we want to add. The solution is homogeneous coordinates. So this is the first time we see, this is the first time we see where homogeneous coordinates actually help us. And I'm not going to bother working backwards, I'll work forwards. And so actually I'll do it this way, so you can see how this works. So 1, 0, tx, 0, 1, ty, 0, 0, 1. That's a translation matrix. So we do that, and let's work it out. X, y, 1, or w, doesn't matter. Let's assume it's 1. Okay, so 1x plus 0y plus tx times w. Awesome. Okay, and if we're not w of 1, the whole thing will scale up based on w, so it works just fine. And then y is going to be 0x plus y plus tx, ty I should say, and then 0, 0, 1. Great, so we can do that, right? We can now use our matrices to translate, to rotate, and to scale. So those three are the most of what you'll do. Now I'm going to briefly show you the other two that are popular, or affine rather, but not popular. But yeah, don't worry too much about them. Reflect. You can reflect on x, and you can basically do a negative scale. You can also reflect on y. Use a negative scale. Y. Okay. So if you know your scale matrix, you can realize that I can do -1 for x, -1 for y, 0, 0, 1, like that. Like I said, I'm going to kind of rush through these. So negative px, 0, 0, y becomes 0, negative py, 0, and then the last one is just w, or 1, just like that. This is not a rigid body because you're inverting it. Okay. And the last one is shear. That's where you stretch things this way. I'm going to show a picture in a minute. You'll see it'll clear things up. And the way you do this, again, I'll just rush through it. 1, cy, 0, cx, 1, 0, 0, 0, 1. And the idea here is px, py, 1. The idea here is you're adding some part of py to x. So this one becomes 1, so it's px plus cx py times plus 0. So you're taking a regular point, but you're adding some of the y value to the x. And then the py becomes px. I should write that differently. cy px plus py. And then the last one doesn't change. So that's how shear works, and it's not rigid body. I'll tell you now, nobody uses shear. Okay, so let's look at a slide. Let's set that up. Oh, right. So here we go. I was just going to show this Wikipedia. So Wikipedia actually has quite a nice page in affine transformations. It shows you what the identity matrix is. Remember, that does nothing. My thing stays original. And then translation. Here's the matrix I explained. Bam. You move to the right. You didn't move y, and so on and so forth. So here's your matrix. Reflection using negative, and this one only had the x negative, so it reflected only in the x. Scale, x is 2 and y is 1, so it stretched double this that way, but didn't change into y, so double x, it's non-uniform scale. Here's the rotate, looks just like we said, everything rotated around theta. In this case, theta is 30 degrees, or pi over 6. Here's what shear looks like, you know, nobody uses it. But this, it's just an x shear with no y shear. You can play with this, some people find it kind of interesting. All right, so I'm going to come back now. Basically, that's all of our affine transformations. So now I'm going to take a break now, but when we come back, we'll learn a bit more how to use them and how to combine them. All right, thanks a lot.